All right, so in the previous video, we kind of introduced solution stoichiometry, how it worked, and we ran through a problem. Now let's really just practice with that. Let's run through a couple practice problems. And I'm going to start with, again, a precipitation reaction, a different one. Um, and the precipitate is iron 3 hydroxide, and then I got a little slop here at the end of the whiteboard. Um, Sodium chloride remains in solution. The sodium ions and the chloride ions are spectators. So the question then is, what volume of 1.500 molar solution of sodium hydroxide would be needed to mix with excess iron 3 chloride solution um, to form 12 grams of solid iron 3 hydroxide? So now, instead of previously, so sometimes I'll say, hey, if I mix this much, this concentration times this volume, how much precipitate will I get? Now, in this case, I'm saying I want to actually form 12 grams of iron 3 hydroxide. So we're given two numbers in our problem, and part of our skills are, okay, well, which one do I start with? What do I use first? How do I start this problem? And so you look at this and say, okay, I've got a given amount of iron 3 hydroxide. It's in mass, so obviously I can't use it yet. I want to make 12 grams of iron 3 hydroxide, the precipitate. And then it's asking me what volume. So volume is my unknown. I'm going to mix a certain amount of sodium hydroxide. I've got excess iron 3 chloride. My question really is about the quantity of sodium hydroxide. So we read through the problem, we say, okay, this is my known, this is my given, this is actually my starting point. So it's similar to what we've done in some others, but we're going to actually work backwards. And so that's part of the skills, is just reading through that and saying, okay, how am I going to start this problem? Oh, okay, sort it out, and sometimes just kind of working it like this and making yourself a little, graphical organizer like that can help. So let's take that 12 grams, let's turn it into moles, and then let's do our stoichiometry. So pause the video, try that. How many moles is 12 grams of iron 3 hydroxide? Okay, so the objective, step one, let's take that 12 grams, turn it into moles. It's iron 3 hydroxide, right? One iron, 3 hydroxides, an O and an H. O is 16, H is 1.01. So each hydroxide is 17.01 times 3. Did a little shortcut on that. So 1 mole of iron 3 hydroxide has a mass of 106.88. So how many moles are there in 12 grams? You cross multiply, and the answer you should get is 1.1123 moles of iron 3 hydroxide. So I had written, of course, 12 grams. Now I've changed it into moles. So now I'm ready to do my stoichiometry. Step 2, stoichiometry. Step 1 was to get into moles so I could do the stoichiometry. Now I go 1 is to 0.1123 as 3 is to x. Okay, so x is 3 times that. So 3 times 0.1123, and I get 0.3368. So that's the number of moles of sodium hydroxide. If I wanted to form the 12 grams, which is 0.1123 moles of iron 3 hydroxide, I'm going to need to use 0.3368 moles, right? Because 3 sodium hydroxides make only 1 of my precipitate molecule. So now let's go back and let's do our final step. The question was, what volume? The question was, okay, and so I know now how many moles of sodium hydroxide I need to make my desired amount of precipitate. Now let's find the volume. I know the moles, and I was given in the problem, it was 0.1500 molar equals certain number of moles. A given number of moles, 0.3368 mole over volume. Well, remember, molar is mole per liter, per 1 liter. And so I can do my cross multiplication, and I'm going to get so I get 0.3368 divided by 1.5 equals. So I get 0.22, I'm going to round a little, 0.225 because my original number only had 0.225. So the volume I get when you cross multiply, solve for V, 0.225 liters. We are in liters because I'm in liters here, right? And so in my molarity equation, the volume is always going to be in liters. Let's convert that, because a lot of times if I'm going to pull out a graduated cylinder and measure out that much volume, it's going to be, my grad cylinder is going to be reading milliliters. So to go from liters to milliliters, move it over 3. So in order to get that 12 grams of precipitate that I need, now I can figure out, okay, I've got this 1.5 molar solution. I'm going to take a grad cylinder and I'm going to measure out 225 milliliters, and I should get my 12 grams. And okay, so so there's one example problem. So now we've worked these problems a couple different ways, forward and backwards. Now let's look at a slightly more complicated limiting reactant problem. Okay, so I have now a reaction. So here's an oxidation reduction reaction. I'm going to take solid zinc metal. I'm going to add it to a solution of copper 1 chloride. How do I know it's copper 1 chloride? Just to give a little review, chloride is always single minus. So what is the charge of copper if it's 1 for 1? It has to be single plus. Copper 1 chloride. So I'm going to add zinc to this solution of copper 1 chloride. And zinc is going to release its electrons. It's going to be oxidized and form zinc 2 plus, because that is the standard state for zinc. I can also confirm by seeing the formula for the zinc chloride. So zinc was solid. It had all its electrons. It now forms a positive ion. The zinc is now in solution. Copper was in solution, and it is now the solid neutral metal. That occurred because electrons were transferred from the zinc to the copper ions. Zinc gave up 2 electrons. Each copper only took 1. Hence the stoichiometry of this 1, 2, 1, 2. And here's our solution. Here's our problem. If I take 15 grams of zinc metal and I add it to 250 milliliters of a 2.050 molar solution of copper 1 chloride, what mass of copper metal should form? Here's my unknown, the product. I've got a known amount of reactant here and a known amount of reactant here. I'm going to turn my mass into moles. I'm going to turn my volume and concentration into moles, and I'm going to figure out which one runs out. And then I can do my stoichiometry. So let's try setting that up. Pause the video, and then I will show. Okay, so I've worked out. I took my 15 grams of zinc metal. I went to the periodic table, found the molar mass of zinc. So 65.39 grams for 1 mole of zinc. How many moles is in 15 grams? And I get this, 0.2294. So to this solution, I'm going to add 0.2294 moles of zinc, of solid zinc. And then I work out my molarity equation. When I solve for moles, moles is the concentration times volume. The concentration was 2.050 molar. I had to change my volume into liters, because this is moles per liter, 0.2500, and I get this, 0.5125 mole. Well, and I got to figure out which one runs out. Well, I've got more of the copper 1 chloride solution. I've definitely got more. I need twice as much. Do I have twice as much? So I can take this number, divide by 2, and this number divide by 1 to figure out what runs out. I'm going to do this the shortcut way. I'm going to say, okay, double that, it would be like 0.45-ish. No, I don't have twice as much. I mean, I do have more than twice as much. I can tell that this is going to run out. Let's do a double check on that. So if I determine that the zinc runs out and it goes to 0, let's double check. Let's double check that because it's going to help me. I'm going to need this anyway. So let me erase this to make some room. So let's figure out how much of the copper chloride I'm going to use. I should find that there's going to be some leftover, right? If I determine that this is my limiting reactant, the one that runs out, I better make sure that this one is going to have some leftover. It has to, right? So I can do 1 is to 0.2294 as 2 is to x. And if I do that, I double this, I get 0.4588 mole. Right, so let's double check. Let's make sure I had enough of this for this to be the limiting reactant and this to be excess. And I can see I start with this and I'm going to have some leftover. This problem didn't ask us to find it. Sometimes we'll even ask what is the concentration of copper 1 ion when it's done. We didn't. So just say, yes, I've confirmed that I'm definitely going to have leftover of this. So I was correct in assuming the zinc is going to run out. That's one way to do a double check. You know, the other way is just to take this, divide by the coefficient to make sure. But I've just confirmed in another way. And I wanted to know how much copper. So I've already done this. 1 is to 0.2294 as 2 is to x. So I already know I'm going to make 0.4588 moles of copper. Now, I wanted to know, though, the problem asked me what mass of copper, because I'm going to take this copper, I'm going to filter it out, and I'm going to weigh it. So what mass should I get? 0.4588 moles of copper should form. Let's convert that to grams. Okay, and we go to our periodic table, we look up the molar mass of copper, and the periodic table tells us 63.55 grams. From the periodic table, 1 mole of copper has a mass of 63.55 grams. If I have this many moles, what is the mass of that? And with some rounding, x equals 29.2 grams of Cu. And there's my answer. So I had a little bit of solution, so we're kind of working. In order to get this number, I had to use my moles, my molarity equation. And so just kind of working that as a practice problem with limiting reactant, a little more complicated. And if I do this, I say, okay, if I mix that amount, I should get 29.2 grams of copper. I can take this, do this reaction, filter my solid copper out, and see how close I get to that. So let's keep practicing.